Hey, this is Leach with Simpson Math, and in this video, we're going to be doing a bit of a deep dive into asymptotes of rational functions. So let's get started. In a previous video, we talked about how to find the horizontal asymptote of a rational function where we have a polynomial divided by a polynomial. Each of those polynomials have a degree, which are referred to as the don and the dod, for the degree of the numerator and the degree of the denominator. We talked about that if the degree of the numerator equals the degree of the denominator, we casually refer to that as an equal power situation because they're the same, and we're just going to look at the ratio of the leading coefficients. And then if the degree of the denominator is bigger than the degree of the denominator is bigger than the degree of the numerator, we refer to that as bottom heavy, and those are easy because they're always just y equals 0. We looked at the why behind that a little bit in terms of a graphical approach and a visual approach, but today we're going to be looking at it a little bit deeper from the perspective of the numerical approach by doing synthetic or long division on it, which is the same process on how we're going to find our asymptotes when it's top heavy. There's a little bit of a vocabulary note. When the function is top heavy, when the rational function is top heavy, meaning the degree of the numerator is bigger than the degree of the denominator, then I'm going to refer to it as just an end-behavior asymptote because the asymptote is no longer a horizontal line. Equal powers and bottom heavy, they are specifically a horizontal line. But if it's top heavy, it could be a linear function, meaning we have an x variable, so the line is diagonal of sorts. Or it could be quadratic or cubic or something else. So to find any of our end-behavior asymptotes, we're going to go through long division or synthetic division, divide those two together in the order that they're shown, and then the quotient without the remainder is the equation of the asymptote that will apply for these other two, and we'll see how that applies, but we'll be able to use our simplified rule going forward. But for the top heavy, we have to do the division. If we compare, for our top heavy situations, compare the degrees of the numerator and the denominator. If they're different by 1, then our end-behavior asymptote will be linear. Difference of 2, it'll be quadratic, 3 for cubic, and so on. And lastly, we can use synthetic division if it works for us conveniently, meaning specifically the denominator is linear and it has a leading coefficient of 1. The rest of the notes here should be a reference page you saw in a previous video where we're about how to find vertical asymptotes and holes and x and y intercepts. Right, let's talk about long division here. So reviewing long division, I'm going to look first back at what we did in elementary school, dividing numbers. I have 14 divided by 2 is 7. From vocabulary, that 14, the numerator is the dividend, this denominator here is the divisor, and the answer of division is quotients. I could also write it this way as well, 14 divided by 2 is 7. The reason why I'm showing you this in both of these forms before I do the long division is sometimes I get confused as to what goes, quote, inside the house and what is on the outside. So I know that if I do 14 divided by 2 like this, I'm going to get a number bigger than 1. I'm going to get 7. So make sure that when you arrange your 14 in your 2 and you go through the algorithm that we get a number bigger than 7. Obviously, we're good with that with numbers, but in a second, if we kind of peek ahead, we're about to do long division of polynomials. And maybe you don't remember which way goes inside that, whether the numerator goes inside the house or not, then just write a simple division problem like this, and then just match. So notice here I have a x cubed term in the numerator, like this 14 is here, and that's what's going to go inside the house, like the 14 was inside the house, and the denominator likewise is on the outside. All right, so just a quick reminder about long division here. So we care a lot about the place values. Obviously this was like, let's say 140, if the number actually was 140. I'm very intentional of them putting the 7 here above the 4 and not that 0 or not the 1. So remember the algorithm on here. So I go, okay, well, how many times does 2 go into 1? It doesn't. Technically, I guess you could say 0. Then I need to look at that complete number 14. So how many times does 2 go into 14? It goes into it 7 times, and so above that 4 we put that 7. And then we multiply. 7 times 2 gives us 14, and then we subtract. If we had a bigger number, like let's say an extra 0 here, it was 140 divided by 2, we would then drop down to 0 and then keep going. In this case, we do have a remainder of 0. We'll see some examples in a bit where the remainder is not 0. All right, so let's do this long division of this polynomial here. So again, notice we set up our house right. So I have my numerator is inside under the house, under that long division bar. And this x plus 4 is on the outside. So what I'm going to do first is I'm just interested in this leading term here. And I'm going to ask myself, how many times does this x go into this x cubed? Or x times what gives me x cubed? Well, that's going to be x squared. So I need to write down my x squared somewhere up here in my quotient. Well, I need to be mindful of my place values. Just like I was very intentional where I put the 7, I'm going to be very intentional where I put my x squared. You can kind of imagine columns here where I have the cubic, the quadratics, the linear terms, and then the constant terms kind of have their spot. So since I'm wanting to write down a quadratic term, an x squared term, I'm going to put it where it belongs in that x squared term spot. All right, now let's basically distribute. I'm going to multiply x squared times my divisor here, but I'm kind of distributing. I'm going to do x squared times x and the x squared times that plus 4. So x squared times x is x cubed, and just like we put this 14 down below, I'm going to do that same thing. So I'm going to put an x cubed here. X squared times 4 is a plus 4x squared. So now I have now multiplied, distributed, and put it beneath, down below. All right, so now we're going to need to do our subtraction, like to kind of color code this and put my little equal to bar, and then I'm going to put parentheses around this entire binomial type thing, and then a subtraction. I would like to see that subtraction so that we're noting that we're subtracting. I've seen some teachers or students in the past that write down a sign change, and I'm going to do that, but I'm going to do it as just like a simple little like note to myself. But I've seen people where like they write the sign changes, and that works if that works for you, cool. But I like to write it this way because it's a little bit more mathematical. We say we're just going to distribute this negative here, but since I can't, we're not like rewriting these things in multiple steps. I'm just going to make a little gentle note to myself that if I were to distribute this negative, this would be a negative here, and this would be a negative here. So I'm kind of floating a negative and just kind of circling it. It's just a little note to myself. So I said here, if we see like a little negative subtraction with the circle or plus with the circle, they're not official math symbols, just a little note to ourselves that that those signs have changed. All right, so now let's add. So if I'm going to add these together, I get x cubed minus x cubed, and so I get a 0x cubed. This is the only time I'm going to write the 0. In future long divisions, I'm just going to have nothing there at all. But right now, I'll go ahead and write the x cubed. So I have 0x cubed, and then let's add 15x squared minus 14x squared, and this should be an 11x squared. All right, I'm not worrying about the plus symbol here because it's not really there because that zero's there anyway. All right, so now we have that done. Now we need to drop down the next place value, the next term. So we copy that down. So now I have 11x squared plus 75x. So now again, I'm just focusing on the leading term. X times what is 11x squared? Well, I have a 1 here and I have an 11, so I'm going to need an 11. And then I have an x, and this is an x squared, so I just need a single x. So it's going to be 11x. So again, 11x belongs in the linear term spot, and it should be the next one over. If you're having to jump over terms, that means you probably might be missing a term or something, or you have terms you might need to combine or something weird. Make sure you have one term for each, for basically each place value for each exponent. And then, also one other note, do you see how we have a binomial for our divisor? So we're going to then place our first digit those 2 terms away. We will have an empty column here, kind of always. There's always is going to go in that first. Let me rephrase that. We have 2 terms here. The first term you're going to write is basically going to be in the second column. Later, when we see 3 terms, it would be in basically the third column over from the left. All right, so now let's distribute that 11x. 11x times x will be our 11x squared. If this doesn't match, you did something wrong. So make sure that that matches 11x squared and 11x squared. 11x times 4 is a plus 44x. Now let's do our subtraction. So all this I'm going to subtract. If you want to, you can make a little note to yourself that this is going to be a minus and this is going to be a minus. When we add up, we get our 0. I'm not going to write that, but we have a 0x squared. And then 75 minus 44, I think that's 39, but I'm going to do scratch work because my brain hurts. 75 minus 44, 6 bar the 1. Oh, silly me. 31. My brain thought it was more complicated for a second there, instead of actually just looking at it behind the curtain. My brain freaked out because I don't see my notes. I was like, I don't have that number memorized. Don't worry about me. Okay, so now I'm going to drop down the 124. I've never been good at mental math, so I had a little mental freak out. It's all good. All right, so I'm going to do x times that. X times what is 31x, and it's going to be that 31. Then 31 times x is, well, 31x. 31 times 4 is 124. I do know that to be true. And then we subtract. And I end up with a 0 for my remainder. One thing I want to point out throughout this whole process, notice I never cared about this 4. In my decision making, I was only interested in this x, that's why I have that highlighted, and then that first term. Down here, I was interested in this x and this term. And then I was interested in this x and this 31x. I was never interested in the 4. The 4 and everything else after just was along for the ride. So it was just this, because I'm needing this term to eliminate, so that way when I pull down, I'm left with another binomial that I'm staring at. However many terms here is however many terms you should be dealing with at once. All right, so now let's process our solution. So this means that if I took, if I kind of forced this cubic to be divided by this linear term, that I would end up with x squared plus 11x plus 31. Well, since we didn't have a remainder, that means it actually divides out evenly. So we could have, basically, it's kind of like x plus 4 is a factor. If you think back to like the possible rational root theorem and all that work that we did there, that's very, very similar. So I kind of expressed this as that factor. So we know that x plus 4 is a factor because it had a remainder of 0. And I was left with a quotient of x squared plus 11x plus 31. So that means that, notice that this would reduce. And so I would be left with this quadratic here. So what I have here, this is just maybe a little bit TMI, but I don't know, I think it's interesting. That notice I'm left with a quadratic, but the function doesn't exist at -4 because I reduce this. So we have a hole here. And again, so if I took this -4 and plugged it into here, it would output a +3. So I have a hole in the middle of this parabola. So holes can exist more or less in a polynomial. Well, it wouldn't then be a polynomial anymore. But we can use our knowledge from our polynomials to graph a polynomial if everything reduces out, but then we would have to address these holes here. So if the denominator reduces out, we graph it like it's a polynomial, and then we just have that hole. Notice one other thing is that we could have just done this with synthetic division. Because our denominator was a linear term, so a linear polynomial with a leading coefficient of 1, that lines up with how we know how to do synthetic division. So we could have just done the synthetic division and got the same thing. I do have a note here that if you want to see some other examples of synthetic division where the synthetic division is a little bit less convenient, we can look at some of those examples. Let me show you what one of those might look like. I need to switch to this button and then this button. I need to make smaller. There we go. Okay, so here, there's the Wikipedia page that I had linked to on the screen that you could peruse just to see how else synthetic division could be. Let me just point out that they're putting it over here to the side. The 3 is kind of on this row in the middle. Same thing, it's all good. But it's interesting that if you have like a quadratic here, that you have this kind of diagonal action you have to deal with. And then if you have a leading coefficient that's not 1, you have this extra kind of division step that you have to deal with. If you're so inclined, look at it. If not, don't. But the important point behind this is that for how we've covered synthetic division, we can only use synthetic division conveniently when it's a linear term, linear polynomial with a leading coefficient of 1. So if it's not that, then we have to do synthetic division. So looking at these next two, oh dearie me, this is not updating. I'm not connected. There we go. Okay, we're back. So if you take a look at these next two here, we have two more that we're going to practice with long division, but notice that the denominators are not linear with a coefficient of 1, so we can't do synthetic division on those. So take a second, and you can pause the video and try these out on your own, and I'll go over them in just a second. All right, let's take a look at this first one. So if I want to do the synthetic division here, again, this numerator goes under the house, and the 2x plus 3 goes outside, and then we go through this similar process. So since this is a binomial, we're kind of looking at two terms at once. 2x times what is 40x cubed? That's going to be a 20x squared. 20x squared then gets distributed to these two terms, and we then have 40x cubed plus 60x squared. Again, this 3 was not entering into my calculations for this 20x squared, but it is just more or less along for the ride, producing that 60x squared. These better be the same, so that way when we subtract, by changing these signs, when we subtract, we're left with 0. So add these together. 54x squared minus 60x squared is a negative 6x squared. Drop down the negative 13x and do the same thing. 2x times what is a negative 6x squared? Well, that's a negative 3x. So this is the first time we're seeing a negative at play, and that's fine. We just put that subtract symbol. Follow that same process. Do your distribution, change your signs, and we have negative 4x. Drop down the negative 6. 2x times what is negative 4x? Well, that's negative 2. Do your distribution, do those match? If they do, keep distributing, and we get negative 4x, negative 6. Subtract them, and we get 0. This other one, if you're needing to work that again, the second one, if you haven't done that one yet, you will also get a remainder of 0. A little bit of a hint. All right, let's check it. So this one, we have a quadratic. It's a cubic divided by a quadratic. So I put my cubic inside. Notice, just side note, this is the quadratic that you have after you do the difference of cubes. So notice here with these 3 terms, sorry, it's a cubic, but I just see 2 terms. I'm missing this squared term and the linear term. So I need to include them. I have to include them. This is not an optional step. I have to include them with this 0x squared and that 0x. So I have to maintain those place values. And then since I have a trinomial up front, we're going to be kind of looking at 3 terms at once. And the first value you should write down should be this 1, 2, 3 terms away. So it should be a linear term. Let's double check. 4x squared times what will give me 8x cubed? Well, in terms of the numbers, 4 times 2 will give me 8. And x squared times x would give me this x cubed. So that's why I'm going to put the 2x down here, because 2x times 4x squared would give me an 8x cubed. And they better match. They do. Keep distributing the 2x to the other 2 terms, and we get this 12x squared plus 18x. Subtract everything. Again, I'm putting my just little notes of my sign changes. Then add everything up, and we get a negative 12x squared minus 18x, and then drop down that negative 27 so we can maintain our 3 terms at once. Then 4x squared times what gives me a negative negative 12x squared. That would be a negative 3. I don't need an extra variable. I don't need an extra x squared, but I do need a negative and a 3. So do my distribution and get these terms. Notice these are negative signs, so when I subtract, they will then become positive. So that's why these become 0, 0, and they all do go to 0. So, because again, that is that means that x squared plus 6x plus 9 is a factor of that numerator. All right, so far all those examples have been examples with no remainders, and of course those graphs would all those graphs produced would simply just be a polynomial with a whole. So now let's take a look at more proper rational functions where we're going to keep having asymptotes instead of it just being a polynomial with a hole in it. So let's see how we deal with these remainders. So you might not remember how to deal with remainders in long division. There's a chance that your memory of long division would just be to write like r, like in this first one, if your remainder was 1, you might just write r1 for like remainder 1. But the proper way to do it is to for your final answer is to write the quotient plus the remainder over the divisor. So let's take a look at these 3 examples. So if I have 13 fourths, so that'd be, I put my 13 inside the house with the 4 on the outside. 4 goes into 13 3 times with 1 left over. So properly, this is 3 plus 1/4. And how do I get that? So here's my 3 in my quotient plus my remainder divided by the divisor. So that's where it's 3 plus 1/4, or since it's a number, it's going to be a mixed number, a 3 and 1/4 for that mixed number. But what about if we have, variables in this polynomial? So do the same stuff, put your values in the right spot, your polynomials in the right spot. X goes into 3x how many times? 3 times. Let's distribute. We get 3x minus 3. Subtract by changing our signs. 3x minus 3x is 0. 2 plus 3 is 5. So now we have a remainder of 5. So how do I write this? We write our quotient plus the remainder divided by the divisor. So that's going to be 3 plus 5 over x minus 1. Okay? So we can do a similar thing here with this quadratic divided by a quadratic. So here we get this denominator on the outside. Ooh, be careful. We're missing the linear term, so make sure we have our plus 0x. Go through the same process. X squared times what is x squared? Well, that's just 1. We still need that 1. That's still a 1 is going to be is our quotient. Distribute the 1. Well, nothing really changes. Do your subtraction. X squared minus x squared is 0. But now I have a negative 7x and a negative 10. So this is my remainder. So we have the similar process. We do our quotient plus the remainder divided by the divisor. Divisor, dividend, my vocabulary term just broke. Divisor, okay, good. Whew, thought I was saying it wrong for the last 20 minutes. Okay, so one extra point I'm trying to make here is just be careful about our signs. So we can say plus, and then just copy the numerator, signs and all. Technically, this does equal. If I factor out a negative from both of those, I can write this as 1 minus this, but look at my numerator. My numerator is now a positive 7x plus 10. So be careful about signs. It's not a requirement. Some things will some people might want you to automatically factor a negative. That leading term is a negative and make it be a subtraction. But if you do something like that, make sure the entire numerator changes its signs, not just the first term. All right. So now that we know how to deal with these remainders by having be plus the remainder over the divisor, let's use them to help us find our asymptotes. So let me remind you of what we talked about at the beginning of the video, that to find end-behavior asymptotes, we use longer synthetic division to divide the 2 polynomials, and the quotient without the remainder is the equation of the asymptote. This is true for when it's top-heavy, bottom-heavy, or equal powers. So this is true for all of our end-behavior asymptotes. So let's first look at our equal powers and our bottom-heavy situations, and let's apply both rules. Let's apply the old rule from like just the bottom-heavy or equal powers part, and then let's also do the long division and see how that works. So let's take a look at this one. So our task is to describe the end behavior of r of x is 4x minus 5 over 2x plus 1. Well, our old method, I would go, oh, well, the degrees on each of those are 1, so that's equal powers. When it's in equal powers, you just do the, you go, I'm going to get that function's digits. And the function's digits is 4 over 2. So 4 over 2 reduces to 2. So I know from our old rule from last lecture that this is going to be a horizontal line of just y equals 2. Well, let's see if we get that when we do long division, shall we? So I do this. So I take our 2x plus 1, put it outside, the 4x minus 5, put it on the inside. 2x times what is 4x? Well, that's a 2. Again, this plus 1, this minus 5, they're just along for the right. I'm only interested in this leading term, the leading terms. I do my distribution, I get negative 4x plus 2. I change my signs, do my subtraction, and I end up with a negative 7 for the remainder. But reminder, what the end behavior asymptote is, it's the quotient without the remainder. Some might say that the quotient would be this entire thing. I'm kind of casually defining the quotient as what's up above, not the remainder. So I'm calling this the quotient, that 2 is the quotient, and then this is the remainder part. So it's a quotient without the remainder. So my quotient is that 2. So that is that is my end behavior asymptote for just y equals 2. So notice we get y equals 2 regardless. I want you to look at something. So we talked about before with this 4 halves of how just kind of as x's get bigger, everything else starts becoming basically irrelevant except for those leading coefficients. But look at this division. This plus 1 could have been plus 100. It could have been minus 1,000,000. It could have been plus pi. It basically doesn't matter other than it exists. It's there, but still it kind of doesn't matter. This can be whatever. This minus 5 can be whatever. It's all about the ratio of these two things. 2x times what gives me 4x? 2. If this 4 would have been a 6, this would have been a 3. If this 2 would have just been a 1, then this would have been a 4. Notice it's all about the ratio here. And since they're equal powers, I don't have an extra variable hanging out. It's just going to be this number. That's why it's still going to be a horizontal line, because I'm not introducing another x. It's just going to be a number, and it's the ratio of those two coefficients. That's why that it's just the ratio of those two coefficients. Isn't that neat? All right, 2 little notes here. I said both methods produce the end behavior asymptote, but if you do the division, you do get the specific remainder, which might be helpful for some questions. And then again, only the leading coefficients a over b had an effect on the quotient. The other values, the other values do matter, but they're just affecting the remainder in terms of this process. All right, let's take a look at the rule for bottom heavy. It was bottom heavy, the easy, it's y equals 0 every time. But let's look at y. So if I have this situation here, this is clearly a bottom heavy situation. So we're going to have the horizontal asymptote is y equals 0, okay, because it's bottom heavy every time. So let's take a look at the math for that. So we're going to do our long division, put this big boy outside, put that 1 on the inside, but we need to include all the relevant place values. So we have a 0x squared plus 0x, then just plus 1. So x squared times what gives me a 0x squared? Well, that would be the value 0. You do your distribution, you get a whole bunch of zeros, subtract them, and you just get 1 for your remainder. Not a lot going on here in terms of long division, but you should be able to see that basically, regardless of what's happening, if I have a larger divisor, I'm always going to have a 0 right here. That's why I'm always going to have a quotient of 0. Then with that, basically, this is my remainder left over. So that's why my quotient here is that 0. Thus, we're always going to have that y equals 0. So that's why moving forward, if we see equal powers, just do the ratio. If you have bottom heavy, just do y equals 0. But now we can see the y behind it. And if for some reason your brain breaks and you don't remember those rules, just do the long division and it should remind you. All right. So for our last set of cases, we're going to need to do some form of division, usually long division. Again, remember it's a quotient without the remainder. And And if it's possible, we can do synthetic division. I'm going to always do the long division. If the synthetic division is possible, I'm going to make a note of that. But I'm just going to do that off to the side because I'm also wanting to make sure we're practicing long division. So let's describe the end-behavior asymptote of this function. Capital K of x is x squared minus 1 over x plus 2. Big brain here, you might want to check just to see if there's anything reduced. Nothing does. But that's more for vertical asymptotes and wholes, but still, just be mindful of that. All right. So since it's a top heavy, the way we go about doing this is division. There's no cutesy way of remembering it. You just got to do the division. So let's do the division. So I'm going to give you a second. If you want to, you can pause it and check it on your own. Do the long division, and then you can also do synthetic division. I'll give you a sec. All right, hopefully you've done it. Let's take a look at how to do it in long division. So with our long division, again, we take our x plus 2, put on the outside, x squared minus 1, put on the inside. Ooh, but be careful. Make sure we have all of our place values, all of our terms in place. So we have a 0x here. X times what is x squared? That's going to be single x. Again, it gets lined up in all of our linear columns. X, let's distribute the x. X times x is x squared. X times 2 is 2x. Do our subtraction. We get a negative 2x. Drop down the negative 1. Do the same process. X times what is negative 2x? That's a negative 2. And then distribute. I get a negative 2x minus 4. But make sure we change our signs for our subtraction. That's where that cancels to 0. And I'm left with a positive 3. So I could rewrite k of x. So this is a rewrite of k of x is x minus 2 plus 3 over x plus 2. If I was to graph, if I was to go into Desmos and graph this function, and then graph this function, they would equal. They would be the same thing. And I'm going to kind of show that off in a minute with a different problem. All right. But what is our end-behavior asymptote? Remember, the end-behavior asymptote is the quotient without the remainder. So it's just that x minus 2. So our end-behavior asymptote is y equals. Make sure we have the y equals part because this is an equation of the end-behavior asymptote. This is y equals x minus 2. Well, note this is not a horizontal asymptote because y equals x minus 2 would be a line with a slope of 1 and y-intercept of negative 2. That is not horizontal. But it is an end-behavior asymptote. So what's happening is as my graph goes to the right, this function is going to be getting closer and closer to x minus 2. As it goes to the left, the graph will be getting closer and closer to that line, x minus 2. You could have also done the synthetic division. Why could have done it? Why was I able to do it via synthetic division? Well, because it is a linear and it has a linear coefficient of 1. So therefore I could have done synthetic division. So would have gotten the same x minus 2 for my quotient and that same remainder. Do be careful. Do you see this this x plus 2? Make sure the number we put on the outside is the negative 2 for that division. All right, so just for fun, I went ahead and graphed it and determined some of the other values just so we could practice our knowledge about graphs here. So we have a vertical asymptote at x equals negative 2. I set I have a domain restriction rather really at negative 2. Nothing reduces, so that's why I have a vertical asymptote at x equals negative 2 right here. This diagonal line right there is the line y equals x minus 2. If you take the numerator and set it equal to 0, you get a positive 1, negative 1. Because this is a difference of squares, rather, I should have said that. So that's, I can factor that into x plus 1, x minus 1, set each of those equal to 0. You get a negative 1 and a positive 1. For the y-intercept, you're going to substitute in 0. So if I put 0 in for both of those, you get a negative 1/2. So we get so for my y-intercept is at 0, negative 1/2. So looking at my graph, I have my x-intercepts in those spots, negative 1, positive 1, 0, and then my y-intercept at 0, negative 1/2. So then we were able to then swoop it accordingly. If you were doing this by hand, you would want to find a few more key points. So, put in maybe, what would this be, like negative 4, see where that is. Put in a few of the numbers just so you can kind of get a good feel of where that goes. All right. One thing that is helpful for graphing is to be mindful of which side where you are in your asymptote. So notice here I'm kind of keeping myself in this quadrant here. So that's kind of what I'm looking at, is like which side of the asymptote am I in. In a minute we're going to see if we're how we're going to decide if it crosses or touches or crosses through the horizontal asymptote. So if it doesn't cross through a touch, I know once I'm on this side I'm going to stay there and then be guided by those asymptotes. All right, so let's do this one. So I have this function. I have a cubic over a linear. This is definitely top heavy. So we need to do some division. So take a second, pause this video, try this one on your own, do this division, see if you can do it in long division, see if you can do it in synthetic division. Ready, set, go. All right, so for the long division, we do get a little bit of a fraction there towards the end. Ew, gross, I know. But we have a linear on the outside, this cubic on the inside, so make sure we're always looking at pairs at a time. So 2x times what is a 2x cubed, but that's just a singular x squared. Do your distribution, and turns out we for a second there we just get 0. I'm going to document that that's a 0x squared. So 2x times what is 0x squared? Well, that's just also going to be 0. And so when you distribute, you get 0. Basically, this almost, I'm imagining like the turn gets skipped, kind of. And now we're down here with negative 23x. I've dropped down my 12. 2x times what is a negative 23x? Ew, Mr. Leach, you made fractions happen. Yeah, I did. We take this, so first a positive times a negative. I need a negative, so that's why it's a subtraction. 2 times what is 23? Well, if I just did 2 times what is negative 23, well, I know that I need that 2 to reduce. I'm going to put a 2 in the bottom. I'm going to be left, I will be left with a negative 23, so I'll put a negative 23 up top. So that's how I end up with that negative 23. Again, I did basically 2 times what, 2 times box equals negative 23, and then just kind of fill in the blank until it works. All right, distribute. I did write this as a decimal just for easier adding, because it's a half, so that's just 0.5. So when I distribute it here, I get a negative 34.5. Negative. This should be a positive. I haven't proofed my notes. This should be a positive here. Yep, see, look at me, silly sign errors. This should be a plus. So that means that this should be a minus. And that's why this should be a minus. I must have graphed it right. Because I graphed it right. Well, that's weird. Okay, so there, fixed. So we have this as a negative 46.5 for my, oops, let me get rid of this here too. All right, so let's put this together. So we have our quotient is 2x minus 23 halves. That's the oh, that's why it doesn't matter, because I didn't graph that. Those are our quotient, and then technically here's our remainder with the correct sign now. So then our end-behavior asymptote is this x squared minus 23 halves. Just FYI, if you wanted to kind of clean this up, because we didn't really like fractions, I mean decimals and fractions at the same time. So you could re-express this 46 halves as negative, this should be negatives here, but negative 69 halves. And then we have this 2 in the bottom right here. So if I kind of do a little bit of a keep, change, flip, keep this, change this to multiplication and flip this over, we see that this 2 actually distributes through that denominator. So that's where we get a negative 69 over 4x minus 6, if you wanted to kind of simplify that a little bit. This is a little bit cleaner, but this is what you come to naturally. Okay, but the point is, this quotient is our End-Behavior Asymptote. Let me get rid of this note over here, which says we can't do synthetic division using our methods, the methods that we learned in our course. So we're not going to do the End-Behavior, we're not going to do that via synthetic division. We'll do it using the long division. So our End-Behavior asymptote is y equals x squared minus 23 halves. So that's just the parent function x squared shifted down 23 halves. So that's this parabola here. Let's look at some of the other things we have going on. We would have a vertical asymptote at x equals 3 halves. We would formally need to check to see if this factors, to see if anything reduces, and I do that here. I show how this does factor. This is a 2x minus 1, not a 2x minus 3. So nothing reduces, so we have no holes. That's why we have a vertical asymptote. We're able to factor this using the possible rational root theorem. And we get x-intercepts of -3, a half, and 4, 0. And a y-intercept of, oops, my y-intercept is written wrong. This should be 0, -4, not -4, 0. All right, so then we can take a look at how this graph works. So there's our vertical asymptote. Here's the parabola. We know we had these 3 dots from our x-intercept, 2 of our x-intercepts and our y. You can plug in a few more dots if you wanted to, but that's why it swoops through here. Comes through along this asymptote because it's basically, it's the End-Behavior asymptote, because as this goes to the left, this is going to be getting closer and closer to this parabola. As this goes to the right, this is going to be getting closer and closer to this parabola. It's just here around in the center where that's all a little bit wonky. So we have, again, close to this parabola, then swooping through, and then going up to this asymptote, and then similarly here. All right, so remember the orange dots, those are just my guides, so they're not actually part of the graph. Just this blue part is the actual function. All right, this next example is a bit of a big picture example, not one to expect on an assignment. I just wanted to review one adding rational expressions, because we're going to need it next. And then I wanted to make some connections to our transformations of the rational parent function. So let's take a look at this. If I have the function t of x is 2 over x plus 3 plus 4. Well, we know from back in the day that this would be, take the rational function, we're going to shift left 3, vertical stretch by factor of 2, and we're going to shift it up 4, and we should get a graph that looks like this. I could be able to get more dots because there's my 1, 2, 2, 1 on either side of those points, and we have that graph. All right? So we know that to be true. But I want to make it fit our form of a polynomial over a polynomial. This is not a polynomial over a polynomial. So how do I fix that? Well, let's add these together, shall we? So when I add these together, I'm going to need a common denominator, because this right now has a denominator of 1. So I'm going to multiply by fancy 1. This term on the left has a denominator of x plus 3. So the term on the right should also have a denominator of x plus 3. So I'm going to multiply by fancy 1, x plus 3 over x plus 3. Do some distribution. Then remember when I'm adding fractions, once you have common denominators, we're going to add the numerators, and we just have one instance of that denominator. So I have x plus 3 for my denominator. Then I'll add my numerators together, combine like terms, and I get 4x plus 14. So this is a bit weird. In a second, I'm going to show you how we can kind of go backwards there. But so these two things do equal. When I put this into Desmos, I got this graph on the left. On the right, when I put this into Desmos, I got this graph. And let's take a look at seeing if this lines up to what we expect it to be. Well, my domain restriction, my red alert here, is that x can't be -3. Nothing reduces, so we don't have a hole. But I do have a vertical asymptote at x equals -3. This is equal powers. So I can just do 4 over 1 for my horizontal asymptote of y equals 4, which we already knew to be true because we're shifting up 4. Oh, and we already knew our vertical asymptote to be true because we're shifting left 3. Then we got a few points from our x-intercepts and our y-intercept. So the numerator equal to 0, solve, you get -7/2. Plug in 0, you get 2/3 plus 4. I want to plug it into the original one here. Or you can plug in 0 here and you would get 14/3. And we can see those points represented here. All right, so both of these match. That's neat. One more little aha is, how could I go backwards here? What if I didn't give you this problem at all? I just said, hey, here's this. Connect that to our transformations. Well, let's do long division. So, or synthetic division, either of those would work. So notice if I do long division, I end up with a quotient of 4, a remainder of 2. So you do 2 over x plus 3. If I do the synthetic division, I get the same thing, a quotient of 4, remainder of 2 over x plus 3. And if I reorder that to how I'm used to seeing this with the rational function part first, notice I get 2 over x plus 3 plus 4, which is exactly what we started with. So sometimes, I underline some of these rational functions could be re-expressed as transformations of the rational parent function. And one of the ways of doing that is through long division here. So I think that's neat. Seeing how we can start with the something from a rational function, smush it together, and the properties, everything plays nicely. And then how would I go back? We'll just force the division to happen through longer synthetic division, and we'll end up with that same thing. Again, that won't work for all of them, because obviously something like this, that's not just a transformation of a rational parent function, because we have a quadratic for a horizontal asymptote instead of just a horizontal line. All right. Two different kind of question types that I want to talk about. The first is, how close is this function, s of x, x squared minus x over x plus 1, to its end behavior when x is 99? So somewhere, I'm kind of imagining a graph here. So somewhere I have some asymptote represented by this orange dotted line. I'm kind of putting this somewhere in quadrant 1-ish. Then I have some curve here from the blue function, the actual function. So I want to know how close are these two. Now, from what we know about asymptotes, should be pretty darn close. Okay, but I want to figure that out. Well, let's think through this process here. So I could find what the function is at that point, this blue highlight. I could then find what the like y value of the asymptote is, and then I could subtract. But notice this distance here, it's going to be this remainder. Let me talk about why that's the case. So recall, I know I'm kind of jumping ahead here. Or I guess I can rewind for 1 sec. Let's go ahead and do our division. Let's do this division here. Let's take our x plus 1, put it outside. X squared minus x, plus 0. Don't forget, we need all the terms, even the constant terms. Do our division. X goes into x squared x. X times, distribute, subtract. We get a negative 2x. X goes in, x times negative 2 is a negative 2x. Distribute, subtract, get a remainder of 2. So our general structure here is that the function equals this quotient plus the remainder over its divisor. So it means the function equals the quotient plus this other piece. I'm going to call this quotient. This quotient is also the end-behavior asymptote. I'm just going to call that q of x just for notation. And I'm going to call this remainder part r of x. So the s function, or really any function for any rational function for that matter, could be re-expressed as the quotient plus its remainder. See that? Here's our quotient part plus the remainder. So if I'm basically wanting to solve, if I'm wanting to find the difference of these two, I don't think I wrote it this way, but if I subtracted q of x from both sides, notice what we're left with. I need to scooch this down just a bit. I had a little epiphany that I did not have when I was writing the notes. that I'm left with r of x, or that's the wrong pink. R of x is going to equal s of x minus this q of x. We can see that visually was what I was banking on, but also we can just see that algebraically here. So to find the difference between the s function and the q function, the s function, which is the actual function, and the asymptote, which is what the question is asking, how close is the s function to its end behavior when x is 99? So here's the s, here's its end behavior. How close is that? Where that distance is the remainder. So instead of having to find the s, find the q, and then subtract them, I'm just going to find the remainder and plug in. So my remainder function, my remainder part is 2 over x plus 1. So I'm just going to plug in 99, which by no accident, I picked a number that would produce nice math. So I have 2 over 99 plus 1, which is 2 over 100, which is 0.02. So the general approach to finding a question like this, find the remainder, then evaluate that remainder at that given x. Last kind of question type you'll see is something like this. Determine, or at least in the notes, determine if t of x touches its end behavior asymptote. So in the last lecture, I talked about, or at least in class I know I did, I'm not sure if I did on the video, but we talked about how horizontal asymptotes are more like guides. Vertical asymptotes are hard, impenetrable walls you can never, ever touch or cross through them. Horizontal asymptotes are guides. I kind of imagine that you have a magnet and you put it under a table, and then you roll like a ball bearing or something, a marble across the top of the surface. But roll it kind of slow enough that marble is going to get closer, and then kind of almost snap to it. I know asymptotes don't actually snap to it unless you touch, but it's kind of line up in line with that magnet. It's a guide. So in behavior, it's going to approach, and basically approaching infinity, going to approach that asymptote. But what if I took that ball bearing and I kind of threw it harder towards that magnet, the magnet being under that table? Well, if I kind of throw it hard enough, it might kind of warp it, and it might kind of wiggle and pass through, but then it will probably come back to it on the other side. So depending upon where this is, I could push it hard enough that it might do a little wiggle and pass through, and then just rolls off the table on the other end. That often happens in the center of the graph. You'll see kind of a little swoopy through. But sometimes I could touch across on the outer part of the asymptotes, and we'll see an example. It'll cross through and then kind of come back up. So it's helpful to know when it does. So step one is to, find the end behavior asymptote. In this particular case, since it's equal powers, then it's just going to be the ratio of the leading coefficients. That's 1 over 1. So my end behavior asymptote is a horizontal asymptote that is y equals 1. Of course, you could do the long division, but it's equal powers, so we'll just do that. I do make a note that if I factor this, which will be helpful later, that I get x minus 3 squared over x times x minus 5. Nothing reduces, but might be easier later. So the idea here is I have this function. I want to see, does it ever equal 1? If your end behavior asymptote isn't a constant, is a horizontal line, then instead of being set equal to 1, I'd be set equal to, that equation, that expression. So it'd be like maybe x plus 3 or whatever it is. So we're going to set the t of x, and we're going to set the 1 equal to each other. And we'll then see what x's make them be equal, if any. So set them equal to each other, and then solve. So this x squared minus 5x is in the way, so I'm going to multiply both sides by x squared minus 5x. My x squared minus 5x reduce, and now I have x squared minus 5x on the right-hand side because this was a 1, nothing grand there. Now I need to solve. Ooh, but lucky me, I notice that when I subtract my x squared to get them together, they actually cancel to 0 on both sides. Then get my x's together. I'm going to go ahead and subtract, or actually rather add the 6x over to the right. When I do, I get a positive x, and that's all my x's together. So now I have just 9 equal x. So 9 is x. So that means that the function t of x intersects the horizontal asymptote, or end behavior asymptote, when x is 9. optionally, I went ahead and graphed that. And so what's interesting here, so we do have two vertical asymptotes at 0 and 5 from these factors. Nothing reduces, so we have no holes. We do have those domain restrictions, or those vertical asymptotes. I have my scale is adjusted every, it's like every little tick mark here is 2 on the x's, but every tick mark on the y's is like a half, because I'm kind of zooming in a little bit. So you see that the function does cross through the horizontal asymptote just barely right there at 9, 1. And so it passes through and comes through, and now it's on the bottom, and now it's on the underside of that asymptote. It actually does kind of peak. It has a localized local minimum at 15. I think it's 15, 0.96. And then from there, it does kind of start going back up. Knowing this number is not a thing you need to know. Desmond told that to me, so I was like, great, and I wrote it down. I was curious where it was, and it found it for me. And so from there, it does kind of start getting closer, 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 closer. So then towards infinity, it'll be getting closer and closer, but always from this underside. I know it will never cross back through. It only will cross or touch here. And I know on this left side, it doesn't cross or touch, just get closer, closer, closer. Other interesting thing, look at my numerator here. When I factor this, I get x minus 3 squared because it was a perfect square trinomial. So look at the x-intercept. It has multiplicity of 2. It's a double root. It touches and turns. So our understanding of roots and multiplicities still applies. And then if you plug in 0 for the function, it's an undefined statement, so that's why there's no y-intercept. Also, we have a vertical asymptote at 0, so we knew that that one had happened. All right, so notice what happened here. So we learned, we were able to pinpoint precisely where the function and the end-behavior asymptotes meet. If you set them equal to each other and you end up with a false statement, that means they will never meet, right? So not all functions will they touch. Sometimes they do, sometimes they don't. All right, lastly, we're going to explore a little bit on Desmos and then wrap it up. So we're going to explore when vertical asymptotes have the concept of multiplicity to vertical asymptotes, which wins when they're on the same x, the vertical asymptote or the whole, and then we'll look at even and odd functions. In class, I'm going to have students create their own polynomial, but we're not going to do that right now. I mean, their own rational function. So let's get that up. All right, so I had this already programmed in over here. So let's take a look at a few of these and we'll be done. So we have, I had the function 1 over x plus 3 that's behaving like we expect that to, just the rational function scooched left over 3. But what happens when I square that? I have 2x plus 3's in the bottom. What happens? It kind of looks like this little like volcano looking thing. So what I want to show you is that if I have an odd number of roots, I misspoke, an odd number of factors in the denominator, basically an odd number kind of vertical asymptotes, the graphs will act in a way that it kind of, hard air quotes here, passes through infinity. It kind of almost wraps through from like negative infinity to positive infinity or vice versa, and kind of passes through the other side of that black hole and comes out on the other end. Hard air quotes. It like crosses through infinity. Like if I have multiplicity of a root, it crosses through the x-axis. But when I have an even number of asymptotes, vertical asymptotes, these aren't end-behavior asymptotes, vertical asymptotes, it kind of, hard air quotes, bounces or touches and turns, bounces off of infinity, kind of goes to infinity, skips over the undefined term, and then comes back from that same side. So if I increase this to a 4th or a 6th or a 22nd, they would be coming from the same side, just a little bit more extreme probably. If I have an odd number, again, they would be on opposite sides of that vertical asymptote. So take a look at this one where I have both. I have 2 x plus 3 factors, so I have 2, when x is negative 3, the function is going kind of bouncing off of negative infinity, hard air quotes, but then when x is positive 3, around the vertical asymptote of x equals 3, they're warping around in opposite directions from them. All right, so there's that part, the multiplicity of vertical asymptotes, which would win. So I have x plus 3 over x plus 3 squared. So obviously the x plus 3's, I could reduce one of the x plus 3's and just have 1 over x plus 3. So this is what 1 over x plus 3 looks like. When I turn this on, am I going to get something different or the same? Let me turn it on. Oh, the red one won. But notice we get just the same thing as 1 over x plus 3. They're the same. Basically, we have a hole when x is negative 3, but we also have the vertical asymptote. So the function is still warping around when x is negative 3, that vertical asymptote. So we have a hole, but the hole basically doesn't matter in this case. All right, last bit, let's talk about even and odd functions. So if I have 1 over x squared, so again, kind of that multiplicity idea, that they're going in the same direction like that, air quote bouncing off of infinity. Do you agree that this would be an even function? Visually, it's symmetric about the origin. If I plug in a negative x, it's just like it hits its shield and just bounces off, just goes dink. If I plug in a negative x, we get 1 over negative x squared, which is just 1 over x squared, so it doesn't change. Remember, even functions, if I plug in a negative x, it doesn't change. Take a look at this one, 1 over x squared minus 9. Visually, we can see it's symmetric about the y-axis, but if I plug in a negative x, it won't change. It just bounces off its shield. So these two are even functions. Well, we know our old friend, the rational parent function 1 over x. It is an odd function. If I plug in a negative x, it produces a negative version of that function, so it would be a negative 1 over x. Or I could take the function, rotate it 180 degrees, and it'd be the same thing. So look at this wackadoodle one. So this too is an odd function. I could take it, grab it, spin it 180 degrees, and it's the same. It has that rotational symmetry. But I could also plug in a negative x and it not change. If I plug in a negative x into the numerator, I misspoke. Plug in a negative x and the whole thing is negated. I got ahead of myself because in the numerator, when I plug in a negative x, the numerator doesn't change. But when I plug in negative x in the denominator, I'll read this in case it's too small on your screen. This is x squared minus 9 all over x cubed minus 4x. The x cubed minus 4x is all in the denominator. So when I plug in a negative x in the numerator just doesn't change. But when I plug in a negative x in the denominator, that whole denominator is negated, which means that this whole function is actually negated. So I have a negative version of that starting out. Whatever, if that's above your head, shrug. But the idea is if I plug in a negative, it does, it basically negates the whole function. So that's why this is an odd function. It's kind of neat looking that it would do that. The reason why that would be helpful is if you know that it's an even or an odd function, if you're trying to pinpoint a few points, like you find an x-intercept, you know that it would have a friend on the other side. This is this weird 1.29973, whatever. If I worked real hard and got that number, then I know it's just on the other side, just with its negative counterparts. So those things happen for us to be able to kind of maybe make graphs be a little bit easier, because if you know that's even or odd, kind of cut your work in half if you're trying to find additional points. All right, so hopefully this helped shed some light into all the different ways we have in-behavior asymptotes, and here at the end, some vertical asymptotes and some of their unique properties. All right, hope this helped. I'll see y'all in the next one. Bye.